For part B, we've been asked to find the displacement of the particle over the interval that's given 0 to pi over 2. So in your notes from the first page, we know that displacement is computed as the integral over the appropriate interval of the velocity. So I'm integrating 6 sine of 3t from 0 to pi over 2. I'm going to make a u substitution. U is going to equal 3t. du over 3 is going to equal dt. U of 0 is 3 times 0 is 0, and u of pi over 2 is going to equal 3 pi over 2. So my new integral, there we go, is the integral from 0 to 3 pi over 2, 6 sine u times du over 3, which is going to make 1/3 times 6 is 2. The antiderivative of sine is negative cosine of u. Remember, I've already updated my limits to be u limits, so I don't have to change back. I'm going to integrate from 0 to 3 pi over 2. That makes it negative 2 times the cosine of 3 pi over 2 is 0, minus the cosine of 0 is 1. So negative 2 times negative 1, which makes a displacement of positive 2. So the displacement is 2, and then there's a second question. If the initial position is 3, so if the position of the particle at time 0 is 3, what is the particle's final position? Well, at the bottom of your last page, final position is initial position plus displacement. So 3 plus 2 makes 5 as the final position. The last part C, we've been asked to find the total distance traveled by the particle. If this were a calculator problem, I would write this integral. The integral from 0 to pi over 2 of the absolute value of 6 sine of 3t dt. I could type that into my calculator. My calculator is able to calculate this result. If I'm going to answer without a calculator, it's going to be my job to figure out on what intervals the velocity is positive, on what intervals the velocity is negative. I'm going to integrate separately, take the absolute values of all my answers, and add those together. So here we go. I know from my answer to part A that velocity is positive on 0 to pi over 3. So I'm going to integrate from 0 to pi over 3, 6 sine of 3t dt. And I'm going to add the absolute value of the integral from 0, from pi over 3 to pi over 2. Of v of t, so same function. I just didn't write it out that time. In absolute value bars. So here's what I'm going to do. I already know from my work on that last problem, part B, what the antiderivative of 6 sine of 3t is. That is negative 2 cosine of 3t. So I'm just not redoing that part with the u substitution. Here, since I'm not making the substitution, I've got t in my final antiderivative. I'm going to keep using t values. 0 to pi over 3. And then I'm going to add the absolute value of negative 2 cosine 3t. From pi over 3 to pi over 2. All right, so that is negative 2 times the cosine of pi over 3 times 3 is pi. Cosine of pi is negative 1 minus cosine of 3 times 0 is 0. Cosine of 0 is 1. Plus the absolute value of negative 2 times cosine of pi over 2 times 3 is 3 pi over 2. The cosine of 3 pi over 2 is 0 minus the cosine of 3 times pi over 3 is the cosine of pi, which is negative 1. It's going to be negative 2 times negative 2 plus the absolute value of negative 2 times 1, which is positive 4 plus 2. So the total distance traveled by the particle is 6. Remember that the whole reason anybody ever tried to invent an integral is because they were trying to find area under a velocity curve, because we thought that maybe that would give us distance traveled. And it used to be, remember in elementary school, middle school, if you wanted to compute distance traveled, you just multiplied the rate times the time. And that was fine back then, because back then we just told you, it was a lie, we told you the velocity was always constant, right? So you drive at 50 miles an hour, the train goes 200 miles an hour. But now we know the velocity isn't always a constant. Velocity can change. So that has to change the way that we compute distance traveled. If we usually multiply rate times time to get distance, but now all of a sudden the rate can vary, we have to break up that what used to be a multiplication problem into tiny little bits of multiplication that we thought of as areas of rectangles that were thinner and thinner and thinner, to simulate multiplying by a function that changes all the time. So just know that that's going to be our idea for chapter 7. What kinds of multiplication, but by functions that change, can we model with an integral? So remember that rate times time equals distance. If the rate's a constant, then it's easy. Rate times time, however long the time is, makes distance. If the rate changes, then we split up the time interval into many, 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 or infinitely many small time intervals, and we multiply by the velocity. Like, we just pick one of the velocities from that interval. And as long as our time intervals get smaller and smaller and smaller, so we end up with infinitely many rectangles, infinitely many time intervals, then that's going to be good enough, and the limit's going to approach the actual value that we seek, the actual area under the curve. So there are lots and lots of problems besides just rate times time to give distance that we can model with and solve with an integral. So take a look at this one from your textbook. If we know the rate of potato consumption in some country, and that rate changes over time, can we still figure out how many potatoes get eaten? So if the rate at which potatoes were eaten, were a constant, we would just multiply that constant by the time interval, and we get a total number of potatoes. But here, the rate at which potatoes are consumed is not constant. We can assume it's constant on a very, very, very small time interval. So the rate at which potatoes are consumed times a teeny tiny time interval is going to give us how many potatoes are consumed in that small time interval. If we then add up all those tiny amounts of potatoes that are eaten over those tiny time intervals, then we get how many potatoes are eaten over the whole, in this case, 2-year time interval that they give us. So notice here, this is what we have. We have a Riemann sum, essentially. So this is a very small change in time. This is the rate function. In this case, it happens to be called capital C of t. And we're going to do these multiplications and add up infinitely many of them. So as I let the number of rectangles go to infinity. So how am I going to write this? I'm going to write an integral from, here we're told that time 0 is the beginning of 1970. So time 1 is the beginning of 71. Time 2 is the beginning of 1972. Time 3 is the beginning of 73. We want the end of 1973. That's going to be time 4, because the end of 73 the beginning of 74 happen at the same moment. And we're going to integrate c of t dt. Because this is a small change in the time interval, dt is an infinitely small change in the time interval as you let the number of time intervals go to infinity. So this you can plug into your calculator, and you can arrive at this answer, which is 7.066. The original rate was measured in millions of bushels per year. So this is millions of bushels of potatoes. So just a word about those units. If C is measured in millions of bushels per year and time is measured in years, then millions of bushels per year times years, the years cancel out, give us units of millions of bushels of potatoes.